We're continuing with Chapter 4 in the statistics textbook. In this video, we're going to go through Section 4.5, which is an introduction to the standard deviation. Okay, as the quote at the beginning of the chapter suggests, it is often helpful to think of the way a list of numbers spreads out around the average. All right, so again, if we come back to the table of contents, we're in the descriptive statistics part, and we've learned about the histogram, which behind a histogram is just a list of numbers. Talked about this in the previous video, right? You have a list of numbers. That's how you create a histogram. All right, and so when it comes to the average and the standard deviation and even the median and the root mean square, you calculate these descriptive statistics from a list of numbers. A histogram and an average and a standard deviation and the root mean squared and the median are ways of describing or presenting a list of numbers. Even the histogram, it's a visual way of presenting something about a list of numbers. And so it is often helpful to think of the way a list of numbers spreads out around the average. This spread is usually measured by a quantity called the standard deviation. So the standard deviation is not the only way to describe how the numbers in a list are spread out around the average, but the main, most usually used metric to describe this property about a list of numbers is the standard deviation. The standard deviation measures the size of deviations from the average. So it's not from the median, it's from the average. Note that as well. It is a sort of average deviation. The program is to interpret the standard deviation in the context of real data and then see how to calculate it. So in this video, we're just going to learn how to see how to interpret the standard deviation in the context of real data. In the next section, we're going to talk about how to calculate the standard deviation. There were 2,696 women age 18 and over in the Haynes 5 sample. So the Haynes study, we talked about that a few videos ago. This was the 03-04 Haynes study where they surveyed a large sample of men and women and got health and nutrition data. They asked different health and nutrition questions, such as weight and height. The average height of these women was about 63.5 inches. So the average height of all of the women in the study, in Haynes 5, the Haynes 5 study, all 2,696 women. That's all of them because the study was ages 18 and over. No one under 18 was part of the study. Okay, and so the average height was 63.5 inches, and the standard deviation was close to 3 inches. The average tells us that most of the women were somewhere around 63.5 inches tall. And the median would kind of tell you the same thing. Remember, the median and the average are two ways of describing the center of the list of values. So you could also cross average out and put median here, and that would make sense as well. But they're saying, okay, the average tells us that most of the women were somewhere around 63.5 inches tall, but there were deviations from the average. Some of the women were taller than average and some were shorter. How big were these deviations? That is where the standard deviation comes in. The standard deviation says how far numbers on a list are from their average. Most entries on the list will be somewhere around 1 standard deviation away from the average. Very few will be more than 2 or 3 standard deviations away. Okay, so just to make sure you have this clear, you have a list of numbers, and if you want to get an idea of the center of those numbers, you can look at the median or the average. Now, if you want to think about how those numbers are spread out around the middle point, then the most common way of doing this is with the standard deviation, which is a measure of spread in relation to the average. Is there another metric that measures spread relative to the median? I don't think so, not that I'm aware of. So the standard deviation is a measure of how much data points are spread out around the center point being the average of the list of numbers, of the data set. The larger the standard deviation, then you're thinking the more spread out the data is from the average. The smaller, then the less spread out the data is. Okay, now it says most entries on the list will be somewhere around 1 standard deviation away from the average. Very few will be more than 2 or 3 standard deviations away. And so don't let this confuse you. You might be thinking, well, wait, if the data is more spread out, wouldn't more entries be more than 1 standard deviation away from the average? No, that's kind of your mind playing tricks on you. It says for any data set, the way you can think about it, this isn't like an official rule, but the way you can think about it is that most entries will be around 1 standard deviation away from the average. So if the data is more spread out, the standard deviation is going to be larger. So no matter what the data set, you can just think about how most entries on the list will be around 1 standard deviation away from the average. Very few will be more than 2 or 3 standard deviations away. Same idea. Well, wouldn't there be, if it's more spread out, wouldn't there be more data points that are more than 2 or 3 standard deviations away? No. If the data is more spread out, the standard deviation is going to be larger. If the data is more spread out, then 2 or 3 standard deviations is going to be a greater distance. The standard deviation of 3 inches says that many of the women differed from the average height by 1 or 2 or 3 inches. 1 inch is a third of a standard deviation. 3 inches is a standard deviation. Okay, so again, in this section, we're just thinking about the idea of standard deviation. We're not talking about how to calculate it. So this is a really important section to understand the concept of the standard deviation. It said that if you took, in the Haynes 5 study, if you looked at the data parameter, the height, they surveyed men and women. We're just looking at the women, all of the women, 18 and older. They got the height of all of the women, and it was in Haynes 5 in 2003 to 2004. We're just looking at those heights, those 2,696 heights. The average of that list of values is 63.5 inches, and the standard deviation was close to 3. Okay, now we come back here. How can we interpret that standard deviation of 3 inches? Well, we just talked about the standard deviation is a measure of how much the data is spread out around the average value. So now we look at the standard deviation of 3 inches. So the data is spread out 3 inches. What does that mean? So one way to look at it is the standard deviation of 3 inches says that many of the women differed from the average height by 1 or 2 or 3 inches. Why are they saying this? Because we just talked about how most of the numbers in a list are around 1 standard deviation away from the average. 1 standard deviation is 3 inches. So, somewhere 1 to 2 to 3 inches, most of the heights of the women are going to be in that range. 1, 2, or 3 inches above or below the average, which was 63.5 inches. 1 inch is a third of a standard deviation. 3 inches is a standard deviation. Few women differed from the average height by more than 6 inches. Okay, so 6 inches is 2 standard deviations. And so what they're saying is if you go past 1 standard deviation away from the average, you're going to have, since most of the data points are within 1 standard deviation, the farther you go away from 1 standard deviation, there's going to be less data points. So now they're saying 2 standard deviations away from the average. It says few women differ from the average height by more than 6 inches, more than 2 standard deviations. There's a rule of thumb which makes this idea more quantitative and which applies to many data sets. Okay? Roughly 68% of the entries on a list, 2 and 3, are within 1 standard deviation of the average. The other 32% are further away. Roughly 95% are within 2 standard deviations of the average. The other 5% are further away. This is so for many lists, but not all. So what they're saying here, this is just a general rule of thumb you can use for any data set. No matter what the data set, the numbers should be in this ballpark. And we're going to see what they're talking about here. In the next chapter, we're going to see that they're talking about a normal distribution, which is like a symmetrical general histogram distribution. That's like you can compare any histogram as relative to that normal distribution. It's like the standard symmetric well-behaved distribution. And so what they're saying is a lot of data sets follow a normal distribution, or they're just some deviation of a normal distribution. And so for any list of numbers, the way you can think about it is, it said most of the data points are going to be within 1 standard deviation from the average. So to put numbers to that, roughly 68% of the entries on a list will be within 1 standard deviation, above or below the average. The rest are further away, obviously, but 95% are within 2 standard deviations. So if we come back here, what they're saying is few women differed from the average height by more than 6 inches. So a woman that had a height that was 6 inches above or below the average, that's going to be rare, because in general, you can think about it as 5% of the entries in the list are going to be above or below 6 inches. So if we take, there was 2,696 women. If we take 5% of that, in general, you can think about around 135 women are going to have heights that are 6 inches above or below 63.5 inches. Figure 8 shows the histogram for the heights of women age 18 and over in that Haynes 5 study. The average is marked by a vertical line, and the region within 1 standard deviation of the average is shaded. The shaded area represents the women who differed from the average height by 1 standard deviation or less. The area is about 72%. So it's close to 68%, right? This isn't that perfect normal distribution that we're going to talk about, but you can see it's a good, the normal distribution is a good estimate. 72% of the data points differed from the average value in the study by 1 standard deviation. And there's that area, right? Remember that area of a histogram represents the percent of data points, as long as you have a density scale, which is usually the case. So because there's a density scale here, any area represents the percentage of data points within that interval. This is 72% of the data points. Well, actually, even if you don't have a density scale, if you compare that area of this area to the area of the entire histogram, it's going to be 72% of the entire area, no matter what. It's just if you have a density scale, you can actually calculate this area using this width and these heights, and you'll get 72% as well. Okay, figure 9 shows the same histogram. Now the area within 2 standard deviations of the average is shaded. So here's that 95% of the data points are going to be within this area. This shaded area represents the women who differed from the average heights by 2 standard deviations or less, and this is 97%. So again, it's actually 97%, but that using 95% as a general rule is a good approximation, it's saying. About 97% of the women differ from the average height by 2 standard deviations or less. To sum up, about 72% of the women differ from the average by 1 standard deviation or less, and 97% differed from the average by 2 standard deviations or less. There was only 1 woman in the sample who was more than 3 standard deviations away from the average, and none were more than 4 standard deviations away. Okay, so let's look at that. 97%, so 0.03 times... Wait, so... Oh, no, okay, yeah. So 97% of the data points were within 2 standard deviations. Greater than 2 standard deviations, there was about 81 women, and there was only 1 woman who was more than 3 standard deviations away from the average. None were more than 4. Okay. For this data set, the 68%, 95% rule works quite well. Where do these numbers come from? They come from the normal distribution, which we're going to talk about in Chapter 5. Okay, now let's work some example problems.